In this video, we will prove the prime number theorem. This video was mainly made for an audience who have already taken a basic undergrad course in complex analysis and are familiar with the concepts of holomorphic functions, meromorphic functions, and contour integrals. The proof of the prime number theorem in this video will be split into 4 different sections. In the first section, we will introduce the notation that we will uphold throughout this entire video. We will present the problem of the prime number theorem and give a reminder to the definition of the Riemann zeta function and show an equivalent definition that will be very helpful in proving the prime number theorem. In the second section, we will introduce the Psi and Psi functions and prove an equivalency between the prime number theorem and their growth. In the third section, we will dive deeper into the Riemann zeta function and build a foundation of properties that we will later use to prove the prime number theorem. And then finally, in the last section, we will analyze the relation between the Psi functions and the Riemann zeta function to conclude the proof of the prime number theorem. The proof to the prime number theorem that we will present in this video is very similar to the proof presented by Stein and Shakarchi in the 7th chapter of their book, Complex Analysis. We have also written our own lecture notes for the proof presented in this video. Both the notes and the book are available in the description of the video. If throughout watching the video you come up with any questions or find any mistakes, feel free to comment down below. Now let us begin the proof. We use the notation where P is a prime number, N, J, and K are indices, X is a real number, and Z and S are complex numbers where sigma is the real part of S and T is the imaginary part of S. Now this notation might look a bit unusual because we're combining a Greek letter and a Latin letter in the same variable. But it is actually the standard notation when talking about a subject, and it was mainly standardized by Hadamard. Now the prime number theorem states that if we define pi n to be the number of primes less than or equal to n, then pi n is asymptotically equivalent to n over the natural log of n. This estimation is very good for large n's, and it also tells us that the prime numbers are spread out with a distribution of roughly 1 over the natural log of n. Now, as a reminder, the Riemann zeta function is a meromorphic function on C with a simple pole at 1 with residue 1 that is the analytic continuation of the series k to the minus iz, where k runs from 0 to infinity. Now Euler actually proved that an equivalent definition to the Riemann zeta function is the series of 1 over 1 minus p to the power of minus z, where p iterates over all the prime numbers. Unsurprisingly, because we want to prove the prime number theorem with the Riemann zeta function, the second definition of the Riemann zeta function will be more helpful to us. Intuitively, when you first look at the prime number theorem, you'd think, since this is a discrete problem, we should probably use discrete methods for the proof. But interestingly, the first ever proof of the prime number theorem was done with the use of complex analysis. In our proof, we will mainly examine how the Riemann zeta function behaves near the line where the real part of S is equal to 1.
In order to prove the prime number theorem, we will need to prove certain facts about pi. For this, it will be helpful to define the function psi, which is another prime-related function. Psi of x can be defined in the following ways. First of all, psi can be defined as the sum of the logarithm of a prime for all prime powers which are less than x. Secondly, psi can be defined as the sum of lambda of j for all j between 1 and x, where lambda is the logarithm of any prime for any prime power. Finally, psi can be defined as the sum for all p prime less than x of the lower floor value of the logarithm of x divided by the logarithm of p, all times the logarithm of p. It is easy to see that the first 2 definitions are equivalent. However, in order to prove that the third one is equivalent, we will need to do a bit more work. First, take psi as it is defined. Then, rewrite the sum to iterate first over primes and then iterate over the respective prime powers. Multiply out the logarithm. Now, the inner sum is 1 for each prime power of p that is less than x. This is by definition the lower floor value of the logarithm of x base p. Now, simply apply a logarithm identity to get the final result. There isn't a particularly easy intuition for the psi function. However, we can still graph it to see some of its key characteristics. We can see that the psi function increases at every prime power, including those which are not primes. So, the psi function increases at numbers such as 16 and 9, where pi does not increase. This next proposition is the reason that the psi function is interesting to us. It states that if psi is asymptotical to x, then pi is asymptotical to x divided by the natural logarithm of x, meaning that the prime number theorem holds. To do this, we first assume that psi is asymptotical to x, and we then want to prove that the limit of pi x times the logarithm of x divided by x is equal to 1. Now, split the limit into the lim inf and the lim sup. For the lim inf, we start off by writing psi in the form that we calculated earlier. Removing the lower floor value gives us a bigger value. The two ln p's cancel each other out, giving us the sum over all prime numbers less than x of the natural logarithm of x, which is by definition pi of x times ln of x. Taking the leftmost and rightmost sides of the inequality, we get that psi of x is less than or equal to pi of x times ln of x. Divide both sides by x, and take the lim inf. The left-hand side is 1 by our assumption, so the right-hand side lim inf is greater than or equal to 1, as we wanted. For the lim sup, start off by fixing alpha less than 1. Then, psi of x is the sum over all prime powers less than x of the logarithm of the prime, so it must be greater than the sum over all prime powers less than x of the logarithm of the prime. This is of course greater than the same sum, with the added restriction that p must be greater than x to the alpha. Now, this sum has an element for every prime between x to the alpha and x, so, by definition, it must have pi of x minus pi of x to the alpha elements. Every element in it is the logarithm of a number greater than x to the alpha, so every element in it is greater than ln of x to the alpha. So, the sum must be greater than the product of these two things. We can now take out the alpha, giving us alpha times pi of x minus pi of x to the alpha times ln x. Now, taking the left hand and right hand sides and doing a bit of algebra, we can get that psi of x plus alpha times pi of x to the alpha times ln of x is greater than alpha times pi of x times ln of x. Now, because pi of x is the number of primes less than x, we know that pi of x must be less than x. In particular, for x to the alpha, pi of x to the alpha is less than x to the alpha, giving us this inequality. Combining with the previous inequality, we get that psi of x plus alpha times x to the alpha times ln of x is greater than alpha times pi of x times ln of x. Now, divide both sides by x, and take the lim sup. X to the alpha minus 1 times ln x is a logarithm divided by a radical, so it must tend to 0. Finally, take the limit of this inequality when alpha goes to 1, giving us the lim sup identity that we desired. So, we've shown that the psi function is powerful enough to prove the prime number theorem. However, the psi function is still not analytic enough to be useful. So, we define the psi1 function to be the integral of the psi function. So, the psi1 function may be thought of as the area under the curve of the psi function. The next proposition is what we will actually use to prove the prime number theorem. It states that if psi1 of x is approximately x squared over 2, then psi of x is approximately x, which, by the previous proposition, proves the prime number theorem. To prove the proposition, we assume psi1 of x is approximately x squared over 2, and we want to prove that the limit of x to infinity of psi of x over x is 1. We can separate this limit into the lim sup and the lim inf. The proof of each of these limits is symmetrical, so we will only prove the one for the lim sup. Take beta greater than 1 or alpha less than 1 for the lim inf version. Now, psi of x can be rewritten as this expression simply because this is an integral of a constant function. Now, remember that psi of x is monotonic, so this is less than this expression where the integral is actually over psi of u instead of psi of x. Because psi1 is the integral of psi, we can collapse this expression to become an expression on psi and the differences of psi1. Divide both sides by x, take the lim sup, finally take beta to 1, giving us the identity that we desired, and concluding the proof. The first property of the zeta function that we want to prove is that zeta has no zeros on the line real part of s equals 1. As a reminder, we already know that outside of the infinite rectangle real part of s is between 0 and 1, the zeta function has no zeros except the so-called trivial zeros, which are the negative even integers. To prove this theorem, we will need multiple lemmas, the first of which is another way to write ln of zeta of s as a sum. First, assume s is real and greater than 1. Now, open the Taylor series expansion of the function ln 1 over 1 minus x. Now, we can rewrite ln of zeta of s as ln of the product form of the zeta function. Now, logarithms turn products into sums, so we can turn this into a sum. Now, we apply the Taylor expansion from earlier on each element of the sum. Finally, we rewrite the sum as a sum on two indices. Because prime factorization is unique, we know that each p to the m appears only once for a specific combination of p and m. This allows us to define Cn to be 1 over m if n is a prime power, and otherwise 0, and rewrite the sum as a one-dimensional sum. Combining everything that we have made, we see an expression for ln of zeta of s, which is true for all s real and greater than 1. This identity is an identity of holomorphic functions on the half plane, which is real part of s greater than 1. We have proven this identity for a line in the domain, so by analytic continuation it must hold in the entire domain, which concludes the proof of this lemma. The second lemma is a trigonometric identity. It is proven algebraically. 0 is less than any number squared. In particular, it is less than 2 times 1 plus cosine of theta squared. Expanding this algebraically, we eventually get the identity that we wanted, which concludes the proof of this lemma. The third lemma is an identity on the zeta function itself. To prove this identity, we first look at the real part of n to the power of minus s, where s is the number sigma plus it. This can be rewritten as e to the power of the natural logarithm of itself. Take only the real part of the exponent out. Remember that the real part of e to the I theta is cosine of theta. All in all, we get that the real part of n to the minus s is equal to n to the minus sigma times cosine of t ln n. Now, begin expanding our expression algebraically. First of all, remember that logarithms turn multiplication into summation. Now, remember that logarithms turn absolute values into real values. Now, substitute in the identity from the first lemma. Combine the sums. Now, substitute in the identity that we have for the real part of n to the minus s. Now, notice that inside the sum is the expression from the second lemma, which is positive as we have shown. So, it is a sum of positive numbers and is positive, which concludes the proof of this lemma. Finally, it is time to prove the theorem. Assume for the sake of contradiction that there exists a t null such that zeta of 1 plus I times t null is equal to 0. All of the following identities are true when sigma is close enough to 1. Zeta has a 0 at 1 plus it null, so its absolute value is less than a constant times the distance from the 0. We can raise this to the power of 4, giving us our first identity. Additionally, zeta has a simple pole at 1, so its absolute value is less than a constant divided by the distance from 1. Again, taking the absolute value and raising to the third power gives us the second identity. Finally, zeta is holomorphic at 1 plus 2 times it null, so it can be bounded by a constant in a neighborhood of that point. Multiplying these three identities, we get that the absolute value of the combination of zetas from the previous lemma is less than a constant times sigma minus 1. Taking the limit of sigma to 1, we get that the expression approaches 0, so the logarithm of the expression approaches negative infinity. However, we've shown in the previous lemma that this expression is always positive, so this is a contradiction, concluding the proof of this theorem.
Like we mentioned earlier, when we are proving the prime number theorem, we are analyzing the behavior of the Riemann zeta function near the line where the real part of S is equal to 1. An important part of this analysis is looking at the behavior of the logarithmic derivative of the Riemann zeta function, which is zeta prime over zeta. To handle this expression, we need bounds on both zeta prime and 1 over zeta. The next proposition is going to give us a bound on the growth of 1 over zeta. Proposition 3.6 states that for every epsilon we have a constant such that the absolute value of 1 over zeta is smaller or equal to the constant times the absolute value of t to the power of epsilon, and this is true for sigma greater or equal to 1 and the absolute value of t greater or equal to 1. To prove this proposition, we are going to use a different proposition, proposition 2.7 from chapter 6 in the book. The first part of this proposition gives us a bound on the growth of zeta, and the second part of the proposition gives us a bound on the growth of zeta prime. Since this video is primarily focused on proving the prime number theorem and it is built around chapter 7 in the book, our main goal here is to help you, the viewers, understand chapter 7 better by giving intuition and going into a lot more detail. For this reason, we will not be proving proposition 2.7 since it is a part of chapter 6 and not chapter 7. But, as we mentioned earlier, a link to the book is found in the description of the video, so if you're interested in reading the proof of proposition 2.7 in chapter 6, which is quite technical, you're welcome to do so yourself. Now, let us prove proposition 3.6. Notice that we know that the absolute value of this product is greater or equal to 1 for all sigma greater than 1 and the absolute value of t greater or equal to 1. We know this is true because the absolute value of this product is a real number, and the last lemma we saw, lemma 3.5, told us that the natural log of this number is greater or equal to 0. Now we can use this to bound the absolute value of zeta to the power of 4 from below with the following product. Because sigma is bigger than 1 and the absolute value of t is bigger or equal to 1, then we can apply proposition 2.7 with sigma 0 equal to 1 to this product. We also know that because sigma is greater than 1, then the absolute value of zeta of sigma is less than or equal to a constant over sigma minus 1. We use the inequality and take the third root to get the following inequality. Finally, we take the fourth root and we get the inequality that we will mainly use to prove this proposition. We will split the rest of the proof into two parts, based on whether sigma minus 1 is greater or equal to a times the absolute value of t to the power of minus 5 epsilon, where a is some positive constant that we will determine later. If this inequality holds, then we know that by the inequality above that we just proved, the absolute value of zeta is greater or equal to some constant times the absolute value of t to the power of minus 4 epsilon. Now we can just choose epsilon to be a quarter of epsilon, and this finishes the proof for the proposition in the case where the inequality does hold. In case the inequality does not hold, then we define sigma prime, which is bigger than sigma, such that sigma prime minus 1 is equal to a times the absolute value of t to the power of minus 5 epsilon. From the reverse triangle inequality, we get the following. Then we apply the mean value theorem. We can now apply the second part of proposition 2.7 regarding zeta prime to show that this is less than or equal to some constant times the absolute value of t to the power of epsilon times sigma prime minus sigma. Because sigma is bigger than 1, we can bound this from above with the same expression where sigma is replaced with 1. Now one last time, we apply the reverse triangle inequality. Now if we take the inequality we just proved and the inequality we have above, but we replace sigma with sigma prime, we get the following. If we choose a to be c prime over 2 times c prime prime all to the power of 4, then if you do all the algebra, which you can find in our lecture notes, you get that this is all equal to a times c prime prime times the absolute value of t to the power of minus 4 epsilon. Now again, like before, we can just replace epsilon with a quarter of epsilon, and this concludes the proof of proposition 3.6 for the second case, and thus concluding the proof of proposition 3.6. We now present proposition 4.1, which states that for any c strictly bigger than 1, psi1 is equal to the following integral. The main thing this proposition gives us is a concrete connection between the Riemann zeta function and the psi1 function. Once we prove this proposition, this connection will let us prove the prime number theorem. It is also interesting to see that this proposition is true for any c strictly bigger than 1 that we choose. So whichever c we choose and we can play around with them, we always get that the integral over the line where the real part of s is equal to c is equal to the psi1 function. Let us remember that in lemma 3.3 we proved the following identity for any s with real part strictly bigger than 1. By differentiating this expression with respect to s, we obtain the following identity for any s with real part strictly bigger than 1. This identity connects the arithmetic of the primes with the analytic behavior of the Riemann zeta function, and it will be very useful later on in the proof of proposition 4.1. To simplify the proof of proposition 4.1, we will first prove lemma 4.2, which is a calculation of an integral for two separate cases. The first part of this lemma states that for any positive c and for any a bigger than 1, then the following integral is equal to 1 minus 1 over a. Let us calculate this integral. First of all, we will define the function f to be a to the power of s over s times s plus 1. For any positive t, we will define the path gamma t to be the following contour. The path gamma t consists of the vertical path st from c minus t to c plus t, and the left half circle ct centered around c with radius t and counterclockwise orientation. Notice that for t strictly bigger than c plus 1, both 0 and minus 1, the poles of f are contained in the interior of gamma t. If we calculate the residue of f at these points, we get that the residue of f at 0 is equal to 1, the residue of f at minus 1 is equal to minus 1 over a. So, by the residue theorem, we get that the integral of f over gamma t is equal to 1 minus 1 over a. Now we know the absolute value of the integral of f over the half circle is less than or equal to the length of the half circle times the supremum of f and the half circle. The length of the circle is equal to pi t since the circle is of radius t. For any s in the half circle, we know that the absolute value of s is equal to the radius of the circle, which is t. Using the reverse triangle inequality, we can prove that the absolute value of s times s plus 1 is bigger or equal than t times t minus 1. This gives us an upper bound for 1 over s times s plus 1 and the half circle. Now, for a to the power of s, the absolute value of a to the power of s is a to the power the real part of s. Notice that the real part of s, which is sigma, is always less than c over the left half circle. And since a is bigger than 1, then we know the absolute value of a to the power of s, which is a to the power of sigma, is less than or equal to a to the power of c. Now the upper boundary of the integral over the half circle converges to 0 when we take t to infinity, which tells us that so does the integral over the half circle. Which finally tells us that the integral over s infinity is equal to 1 minus 1 over a, which is what we wanted to prove. The second part of the lemma states that if a is between 0 and 1, then the integral is equal to 0. We will define the same f as we did before. This time we'll take the contour gamma to be st and the right half circle centered around c. In this case, f is holomorphic in the interior of gamma t, so by Cauchy's theorem, the integral of f over the contour is equal to 0. Notice that if t is bigger than 1, then we can bound from above the absolute value of the integral of f over the right half circle with the exact same bound we used for the left half circle in the proof of the first case of lemma 4.2. The main difference now is in the first case of the lemma, we bounded the absolute value of a to the power of s, which is equal to a to the power of sigma, with the bound of a to the power of c. Now, in this example, we can still use this bound because even though sigma is now bigger than c, we know a is between 0 and 1, so a to the power of c is bigger than a to the power of sigma. This tells us that if we take t to infinity, then the integral over the right half circle is 0, which means that the integral over s infinity is equal to 0, which is what we wanted to prove and concludes the proof of lemma 4.2. Now we have all the tools we need to prove proposition 4.1. We know psi of j can be written as the series of lambda n times the indicator of whether j is bigger than n. By definition, psi1 of x is the integral of psi1. We can replace the psi inside the integral with the identity above. Since everything converges, we can use Fubini's theorem to switch the integral and sum. Since the indicator is 0, when u is smaller than n, then the integral is just the integral of 1 from n to x, thus giving us the following sum and identity that we will use to prove proposition 4.1. We will show this is equal to the following integral. Remember that at the start of section 4, we said that the logarithmic derivative of the Riemann zeta function is equal to minus the series of lambda n over n to the power of s. Using Fubini's theorem, we can switch the sum and integral. Now the integral we get might look familiar because it is exactly the integral we saw in lemma 4.2, where a is equal to x over n. So now, if x is bigger than n, then we know the integral of this is equal to 1 minus n over x, and otherwise it is equal to 0. And then finally, we move the x to the right, and from the identity above, this is equal to psi of x, and this proves that for any c strictly bigger than 1, the following integral is equal to psi of x, which concludes the proof of proposition 4.1.
We have now gathered enough theorems, propositions, and lemmas to prove the prime number theorem. In order to prove the prime number theorem, we will simply show that psi1 is asymptotical to x squared over 2, which we have already shown to be a powerful enough result. Define the integrand big F of s as the integrand from the previous propositions. For this proof, we will need to define the contours real part of s equals c and gamma of t, where gamma of t is the contour which is on the line real part of s equals 1 when the imaginary part of s is greater than t, and otherwise real part of s is equal to c. Now, from the previous proposition 3.6 and 2.7 from the book, we can know that the absolute value of zeta tag over zeta is less than a times t to the power of eta for any eta greater than 0. In particular, in the green region trapped between gamma and real part of s equals c, we can see that the integrand f is zeta tag over zeta multiplied by 1 over s times s plus 1 approximately. And since the real part of s is bounded, we can know that s over s plus 1 is approximately t to the power of minus 2, and conclude that the absolute value of the integrand f is less than some constant times t to the power of minus 2 plus eta. As we've already seen, psi1 is equal to the integral over the line real part of s equals c of f of s. Our next goal will be to show that it is also equal to the integral over gamma of t of f of s. To do this, we define gamma c of t to be like gamma of t, except that it stops when the imaginary part of s is equal to c, and then goes back to the line real part of s equals c. By Cauchy's theorem, we can see that the integral over gamma c of t is equal to the integral between c minus ix to c plus ix of f of s, as they trap an area which is holomorphic under the function. Now, if we take the limit c to infinity, we get the equality that we wanted. Note that the straight lines at the end of gamma xc have no impact on this final integral because they are in the green region, which decays exponentially, as explained before. Now that we know that the integral over gamma of t is equal to psi 1, we will once again want to transform this contour into another contour. To do this, we define the contour gamma of t delta, which is like gamma of t, except that instead of steering to the right to c, it steers to the left to 1 minus delta. We will choose a delta such that in the rectangle, which is real part of s is between 1 minus delta and 1, and imaginary part of s is between minus big T and plus big T, there are no zeros of the zeta function. The reason why this is possible is because we have proven earlier that the zeta function has no zeros on the line real part of s is equal to 1, and this is simply a small area around that line. And with the function being holomorphic, little disturbances will not create additional zeros. The area which we created in which the zeta function has no zeros is marked green on the chart. Now, using the fact that zeta has a simple pole at 1 with residue 1, it is possible to compute that the integrand f has a simple pole of residue x squared over 2 at 1. So, using the residue theorem, we can conclude that 1 over 2 pi I times the integral over gamma of f is equal to x squared over 2 plus 1 over 2 pi I times the integral over gamma of t delta of f. This is because the contours gamma of t and gamma of t delta trap between themselves the singularity at 1 and no other singularities of f. Of course, we've already shown that the left-hand side of this equation is equal to psi 1 of x. So, in order to show that psi 1 is asymptotical to x squared over 2, and by extension prove the prime number theorem, we only need to show that the integral over gamma of t delta of f of s is asymptotically less than x squared over 2. In order to do this, we split the contour gamma of t delta into the 5 contours gamma 1 through gamma 5. It will now suffice to show that the integral over each of the sub-contours is asymptotically less than x squared over 2 to prove the prime number theorem. For gamma 1 and 5, remember that the absolute value of zeta tag over zeta can be bounded by t to the power of 1/2 times some constant, as we've shown in proposition 3.6. Now, over gamma 1 and 5, we can split the integrand f into 3 parts. The first of which is the zeta part, which we have already shown to be less than t to the power of 1/2 times some constant. The part x to the s plus 1 is of absolute value x squared precisely. And the denominator 1 over s times s plus 1 is asymptotical to 1 over t squared because this is on the line real part of s is equal to 1. All in all, we can conclude that the absolute value of f is less than t to the power of 1/2 over t squared times x squared, giving us the following integral. However, the right-hand side of this integral inequality contains the tail of an integral which converges, and since it is a convergent integral, we can choose a t so large such that the integral is less than epsilon. So, the integral over gamma 1 and 5 is less than epsilon times x squared times some constant, which is asymptotically small enough for us. For the rest of this proof, big T is fixed to be the t that we found for gamma 1 and 5. Now, on gamma 3, the absolute value of x to the power of 1 plus s is equal to x to the power of 1 plus 1 minus delta, which is equal to x to the power of 2 minus delta. Now, because the integrand f without the part x to the s plus 1 is holomorphic over gamma 3 by the definition of delta, we can conclude that it is bounded on it by some ct. So, the absolute value of the integral over gamma 3 of f is less than that ct times x to the power of 2 minus delta, which is asymptotically small enough for us. Finally, over gamma 2 and 4, we can use the same ct trick and expand the integral to be less than or equal to the integral from 1 minus delta to 1 of x to the 1 plus sigma d sigma. Now, if we continue expanding this, we can see that this is less than or equal to some other constant times x squared over ln x, which is asymptotically smaller than x squared over 2, which is asymptotically small enough for us. So, we've proven that over every one of the parts of gamma t delta, gamma 1 through gamma 5, the integral is asymptotically smaller than x squared over 2. So, the total integral over gamma of t delta of f is asymptotically less than x squared over 2, which as we have shown earlier means that psi 1 is asymptotical to x squared over 2, which as we have shown even earlier means that pi of x is asymptotical to x over ln x, proving the prime number theorem.
We hope that you enjoyed the video, that the explanations were clear, and the animations helped with intuition, and thank you for listening until the end.